Okay, so the data set that we're going to use as a t-test example today is what's called the prison isolation experiment. And what they were trying to do in this experiment, it occurred in Raleigh, North Carolina, where inmates volunteered to be involved in what's called an isolation experience. The idea is that through this treatment, this isolation type of treatment, the researchers wanted to know how it would affect deviant behavior, specifically the need for control or their rebellion against control. So that's the measure that was given, which is part of the Minnesota Multiphasic Personality Inventory. Okay, so what we're measuring is that need for control and the need for rebellion against control. Okay, and that gives us a composite score. The higher, the more rebellious, lower, the more need for control. Okay, and of course, what we want to see is those scores to be lowered instead of the rebellion score. And so they did this in 3 phases. So they had a pre-treatment, post-treatment, and then they did it 2 more times, just to kind of have some more longitudinal data. Okay, and so what we're looking at is a pre-treatment, a treatment in place, and then a post-treatment measure. Okay, and so what we have is in this data set is a paired samples data set. If we look at the data set right here, which I did share in the Canvas page, what we have is we have pre-post 1, pre-post 2, pre-post 3. And then, so we can run some additional analysis. I put this other category of participants, and 1 is going to be group A, 2 is going to be represent group B. So I'll show you how that works here in just a second. So what I'm going to do is I'm going to go through and I'm going to use Spss to analyze this data using different t-test modalities. And then we're going to watch some videos on how to run a t-test on using Microsoft Excel and Microsoft Google. And then I'm going to see how you guys do with this data set individually, while in groups, I should say. So that's kind of where we're headed. And so let's get started on that. So I'm going to pull up our data set in Spss, which I have it here. So remember, this is the variable view. This tells you what type of variable it is. We can see we have 1, 2, 3, 4, 5, 6 scales, which is pre-post, pre-post, pre-post. And then we have a group 1, nominals, okay? No worries, right? It's just good to have you here. Thank you. And so that's how the data is. And then if we go to data view, this is the scores. And then we have the participants 1, 2, 1, 2, 1, 2 for later. But as I noted, this is a paired samples t-test because we're measuring the same person over time. So we have multiple measures of the same person. So that's called a paired t-test. So let's go up here and we can hit analyze. And in here, it's under compare means. And we're going to do what we call a paired samples t-test. Okay, let me reset this. So let's just go with the first clinical run. So we're going to put pre-test 1 and post-test 1 in our variables. Okay. Now, when we're doing a paired samples t-test, it's easiest to just do the standard deviation of the differences when it's calculating standardized. Don't worry about the terminology. It's just know that this is the one that works with the equations we've learned in this class. Okay. And then we look up here at options, make sure we're set at our 95%. Remember, this is P less than 0.05. And so this is 95%. So we're looking at our 95% confident intervals based on that. Okay. So let's see what happens when we run this test. All right. So here we have our test results. And you know what? I think the best thing to do would be able to do this. Let's do this. Okay, let's read this and allow us to mark it up as we go. All right. So this first table gives you the descriptive statistics that you need. So you can see pre-test we were at 71, and it does look like the mean score did go down, which is what we want, because we want them to score lower on this test. Okay, we have an N of we have an N of 13 for both. Okay. And we can see the standard deviations are very similar and the standard error of the mean. We have that right here. So, okay. So in this next one, it just gives us the correlation. Okay. The correlation, which we will get to, let's not worry about that right now. All right. So this is the actual test that we're going to look at. And what we're going to see is that when we see the difference between pre-test 1 and pre-test 2, we get 5.38. That's the mean difference. Okay. Our standard deviation for the two is 12.36, which is a little bit higher. You'll notice that. And then let's get to the actual t-test. So let me show you how this would write out. So we have a t. And remember in here, we put the degrees of freedom. So that is here. And this is going to equal the critical value of 1.567. So that's this number. Okay. Now remember, there was a mention of tables last week. That using the tables, you use this 1.567 with the degrees of freedom to see if the p-value is under 0.05. But we actually have it right here. Now, we have the significance levels right here. Now, the thing that we need to decide is if we're going to use a one-tailed test or the two-tailed test. So if you remember, I said that we want scores to be lower, okay? We're not saying scores will change. What we want to see is that the scores are lower than the pre-test. So we're going to use a one-tailed test to see if that worked out, because it's only going to test for one side of the distribution, okay? So in this case, our P equals 0.071, okay, which is greater than 0.05. Which then what we would need to do in this case then is we would need to accept the null hypothesis and reject the alternative hypothesis that there is no difference because of this. There is no significant difference between the pre-scores and the post-scores. That would be our interpretation, okay? Now, there is one way you can always tell whether or not there's going to be significant differences or not without even looking at this part, okay? And I'm going to show you how. You can actually look at the confidence interval. If your confidence interval starts with a negative number, your statistic will always be non-significant. Because in this case, because there's no negative potential values that a person can score in, then that would make this lower range impossible. Okay, no one can score negatively, so you can't have an actual population mean less than 0. So whenever your confident interval starts with a negative number, you can instantly state that it's a non-significant finding. Okay, so that's another way you can look at this test here. Now, because it's non-significant, it makes our effect sizes pretty useless. We can't use them right now. But when you're looking up the effect size, the one you want to look at is the point estimate. So the effect size is 0.43. We look it up on a table and we find that it was a very small effect size. But again, we can't use these effect sizes because once again, and this is, we see our confidence intervals, because our confident intervals start with a negative number, that means that they're non-significant and there's really no effect, okay? So that's the paired sample t-test. So what we can say at this point for this example is that the treatment, the isolation treatment, at least in the first run of the experiment, did not have an effect. It was non-significant, okay? All right, so let me get out of there. Does anybody have any questions about the paired samples t-test?
No.
Okay, no, okay. All right. Now, let me. All right. Okay, thank you, Christy and Novia. All right, so the next one that I want to demonstrate is the independent t-test. The independent t-test is when you have individuals that you want to compare with each other. So like I said, in this data set, I set up participants. 1 equals group A and 2 equals group B. And so we're going to compare in one of the time periods if there's statistical differences between group A versus group B. And as I said, this is what we call an independence t-test. So again, we're going to go up here. We're going to go down to compare means, and we're going to do independent samples t-test. Okay. I'm going to put my grouping variable right here. I'm going to define groups, and remember they were 1 and 2. So it's going to do group A, group B here. Okay. And let's just do the post-test 3. Okay. I'm going to request effect size. I'm going to look at options, make sure that it's at the 95 confidence interval level. And I'm going to hit continue and hit OK. All right. So this one will require a little bit more space. All right. So let's go through on how to read this one. Okay. So again, here we have our statistics. Hi, Sherry. Yeah, I see your hand is up.
Is that the R scale? Is it called the R scale where you download that R? Is that what you're using right here?
I'm actually using SPSS. This is just a different, it's kind of like R. It works very similar, but it's just,
yeah.
Yeah.
Okay. All right. Yeah. Thank you.
You're welcome. All right. So we can see again, here we have our statistics. We have group A, B, 7 in group 1, 6 in group B. We can see that there's definitely a mean difference, and there's differences in the standard deviation. The standard error is very close to each other. So let's go through and first kind of divide this, because reading this test, you have to read it in two forms, okay? And you kind of split it right here down the middle, all right? Because an independence t-test, the most accurate version is if equal variance is assumed the same. But there is another test when you don't have equal variance. Now, what I mean by equal variance is that, is there a statistically significant difference between how much the scores differ in group A versus group B, okay? And so this does an F test, which is an ANOVA, just to give that test statistic. And the reason that we do an ANOVA for this is because ANOVA specifically tests differences in variance, okay? It's gonna give us a test statistic of 2.035 and a significance level, of 0.18, which again is greater than 0.05, all right? Now, here's the way you want to think about this. If there is no statistically significant difference in this F test, okay, in the variance, then you can assume equal variance as it can be assumed, okay? So non-significant Levine's test. This is called the Levine's test up here. It makes it so you can assume that the variance is equal. If this is less than 0.05, this statistic right here, then you would use this test here. But in this case, because the variance is equal, we can ignore this area here, okay? All right. So once again, in this case, we only asked if there was a difference between group A or B. We didn't predict which would be less or lower. So we're going to use the two-sided p-value, okay? So once again, the way we would write this out is T, degrees of freedom of 11, okay? And just as a reminder how you get to this 11, this is 7 plus 6, which equals 13, minus 2 for each group. And we get 11 degrees of freedom, okay? All right, so again, 11 degrees of freedom up here. Our test statistic is 1.791. And our P equals 0.101, which again is greater than 0.05. So once again, we would accept the null hypotheses that there is no difference between group A and group B in this case. Now let's give an example, because this is a good example of what if we thought that group B would be less than group A. So then we would have a one-sided t-test. And then again, even though the statistics would be the same, and this is the importance of determining whether a test should be one-tailed or two-tailed, because in the directional one, we get a p-value of 0.05, which 0.05, of course, is equal to 0.05. So in this case, if we were predicting that one of these would be lower than the other, then we would reject the null hypothesis in favor of the alternative hypothesis that there are differences between these groups, that group B did significantly lower, have statistically lower scores than people in group A. Okay. Sherry, you have your hand up.
I'm sorry. And this is where the study starts, you start doing another study on it, right? When it's like that?
Yeah, I mean, this is what
like an ongoing, what is it called that we were saying, ongoing hypothesis, and then you would start another one, right?
Right. So if this was being done by a researcher, they'd go through and they'd interpret this data, right? And they would then write it up, and then they would probably get other research questions based on this that they would continue their line of research. But in the science field, someone would go publish the significant results, and then other researchers would try to replicate it. And so it kind of, there's two prongs to that question is, yes, you would figure out what wasn't answered. And then also you want to publish so people can try and replicate your results. So yeah, good questions. Now down here, we can see that we can use the different effect sizes. And again, for sakes of intro to statistics, the one that we'll be paying attention to is the Cohen's d, and we're going to be paying attention to this number right here. Okay. Now you'll notice that this is negative. Again, this one is negative because it does it on a two-tailed confidence interval range. So just so you know that. All right. So let's look at this for just a second. Okay. Let's look up. We'll do this together. Let's look up. All right. And I did this because I think this is the easiest way to just remember if you just Google it. So effect sizes for Cohen's d is, and let's put these in R. And we'll put it over here. All right. So again, when looking at the Cohen's d, you want to look at the point estimate, not the standardizer, okay? So ours is 0.996. So 0.2 to 0.5, whoops, I did it again. Anywhere from 0.2 to 0.5 is considered small. 0.5 to 0.8 is considered medium, and anything above 0.8 is considered a large effect size, meaning that there's large differences between the group. And as you can see, we have 0.996, which lays somewhere over here. So we know that we have a large effect size, meaning that statistically, when we take variance into account, how much people vary between the two groups, that this difference between 69.17 in group B and group A, 83.43, even though logically they seem big, we know that when you count for variance, that these two groups are truly significantly separate from each other. Their scores are truly significantly different from each other. Okay, so that's how you would interpret the Cohen, the effect size. All right. Okay. All right. Keep that. All right. So let's go back. Did I get rid of this? All right. Okay, so now what I'd like to do is I'd like to transition, and I'd want us to watch the two videos, YouTube videos about how to do a t-test with Excel and how to do a t-test with Google Sheets. And so, and then I'm going to turn this data over to you all to kind of practice in whichever modality that you're using the most. So I'm going to stop and we'll watch the first one on how to do it with Excel. And then we will go from there.
Hi, it's Chester at Blue Peak Training. And in this video, we're going to learn about performing a t-test in Excel. Now, I am going to assume that you've come to this video because you know what a t-test is and you understand the terminology. All I want to do in this video is quickly show you how to perform the t-test. So the first step is to install the Analysis Toolpak add-in. And to do that, we go to File, Options, Add-ins. Down here it says Manage Excel Add-ins. Click on Go and tick Analysis Toolpak. If it's already ticked, then it's already installed. Click on OK. Go to the Data tab and you should see a little button in the Analysis group called Data Analysis. Click that. If you scroll down this list, you'll see your t-test options here. Got 3 different methods that you can use. So the dialog box is the same for all 3 methods, so I'll just start with the first one. Click on OK. So you've got your 2 input ranges, which you select. Got your assumed alpha value, which you can change if you like, and then you choose your output range, which I'll say is here. Click on OK, and there is your t-test. If you wanted to use a different method for your t-test, then use the same steps, data analysis. So I'll go for 2 sample assuming equal variances. Click on OK, choose my ranges, choose my output range. And I get the results for that method. Now this p-value, which is the thing you'll probably be most interested in, you could also calculate using a function. So there is a function called t.test. First argument is array 1, so we select the first sample, comma, and then our second sample. Tails, so you choose whether you have a 1-tailed distribution or a 2-tailed distribution. We'll say 1-tailed for this, comma, and then you choose the type of t-test you're doing, and because I want to mimic what we're doing up here, I'll choose paired, comma, and you'll see that I get the same result as we've got here. I could do the same for a 2-sample with equal variance test, so equals t.test. Choose my samples. So it's a 1-tailed distribution, and we'll go for 2-sample with equal variance as we have up here. And so you can see these 2 results are the same. Okay, that's all I wanted to cover in this video. Hopefully that's useful. If it is, please subscribe, and I'll see you next video.
Okay, so that is using Excel. So now let's take a look at those who prefer the Google Sheets.
All right, so we're going to go over how to do some statistics when we have two treatments that we are trying to see if there is a significant difference between them. So I've got treatment A and treatment B. We've got the data here. Our independent variable then is the treatment. Our dependent variable is whatever measurement here. So for our lab, treatment A would be a pH of something and treatment B would be a different pH. And then these measurements would be seedling growth in millimeters or centimeters. And now we want to know, we're going to do first some descriptive statistics. So this we've done in previous labs, but let's just write these down. It's standard deviation and average for our two treatments. So to do this, I'm going to hit equals. I'm going to start typing average. Here we have average. I'm going to select everything here, and then I'm going to hit the check mark in the bottom right, and then that gives me average. And then for standard deviation, it's STDEV. I'm going to select those values. Oops, hit the check mark. And there we go. All right, and it would repeat then for the next column. All right, so I already have then some descriptive statistics. My average for treatment A is 9.95 with a standard deviation of 4.7. And my average for treatment B is 6.65 with a standard deviation of 3.47. All right, but now I want to do a t-test. And for the t-test, I'm going to use both of the data, both columns. So I'm going to do equals t-test. All right, and there it is. I'm going to take range 1, which is this one, and select that, and then hit a comma. Now I'm going to select range 2, and I'm going to select the second one, and comma. If we don't know, oh, looks like I need to make that C21. If we don't know, or we don't have an expectation as to which will be greater, then the tails will be 2. And then the type is going to be 1. And what this is going to give me is a p-value. So here I have a p-value of 0.005. And so for my results, I can write the average for treatment A, the standard deviation for treatment A, again, those for treatment B. And then I can say I performed a 2-sample t-test to test if there was a difference between the two treatments. And my p-value was 0.005. And in this instance, I would say it is a significant difference because it is below our alpha of p.05. And I would reject the null hypothesis. All right, so there's still one other thing that would be important to do, and that is going to be make a graph. So I'm going to put my labels for treatment A and B, and then I'm going to write in those averages 4.718106. I know, that's probably plenty. And that's not the average. Oops. 9.95 is the average, and 6.65 is the average there. And now I'm going to make a bar graph. To do that, I hit the plus in the top right. I hit chart, and I'm going to do a column chart here. And then I'm going to format it for how I want it. So I do not want a legend. I can put in horizontal axis title. Well, actually, I think what I'll do is I will take the legend and I'll move it to the bottom. And that'll give me treatment A and treatment B. And then my titles, left vertical axis title, I'm going to put length of seedlings in millimeters. All right, and that's all the information I need. There's my graph. I can then move that into a word processing document and give it a figure caption.
Chasing that A in one proofreading, grammar